Welcome to a deep dive into space complexity. In this video, we'll explore how to measure the memory usage of algorithms. It's essential to understand how much space your code needs, especially when dealing with large datasets or limited resources. Let's get started by understanding memory usage of algorithms. So, what exactly is space complexity? Space complexity is a measure of the amount of memory or space that an algorithm requires to run, as a function of the size of its input. In simpler terms, it tells you how much memory your algorithm will need as the input grows larger. It primarily measures memory usage during the execution of your code. This includes the space used by variables, data structures, and temporary storage. It also considers auxiliary space, which is the extra temporary space used by the algorithm beyond the input itself. Space complexity is typically expressed using big O notation, which provides an upper bound on the growth rate of memory usage. Visualize three memory usage bars. First bar shows constant space, which is denoted as O of 1. The second bar shows linear space denoted as O of n. The third one shows quadratic space denoted as O of n square. This is algorithm complexity versus memory usage graph. Now let's delve into some common types of space complexity that you will encounter. First is O of 1 constant space, which uses a fixed amount of memory regardless of the input size. For example, consider this Python function findMax that finds the maximum value in an array. It only uses one variable, max value, to store the maximum number, irrespective of the array size. Next is O of log n logarithmic space. The space grows logarithmically with the input size. Next, look at this Python function binary search. The variables low, high, and mid take up constant space. Since the function halves the search space in each step, the space complexity is O of log n. Next is O of n linear space. Here, memory usage grows linearly with the input size. For example, see this Python function duplicate array, where the size of result array increases linearly with the input array. Therefore, the space complexity is O of n. Last is O of n square quadratic space. Memory usage grows with the square of the input size. For example, consider this Python function create matrix that creates a 2D array with n cross n elements. The space required increases quadratically with the input size. Hence, the space complexity is O of n square. It's important to differentiate between auxiliary space and total space. Auxiliary space refers to the extra space used by an algorithm, excluding the input space. On the other hand, total space is the sum of the input space and the auxiliary space used by the algorithm. When analyzing algorithms, we often focus on auxiliary space, because it represents the additional memory needed beyond the input itself. Total space consists of input space and auxiliary space. Input space is required by any algorithm. Auxiliary space is the extra memory used during execution. Let's explore how recursion impacts space complexity. Recursive functions use call stack memory for each function call, significantly affecting space complexity. For instance, consider this classic Python function factorial n. In the base case, if n equals 0 or n equals 1, it returns 1. In the recursive case, it returns n times factorial of n minus 1. The space complexity here is O of n, due to n recursive calls stored in the memory simultaneously. You can visualize the call stack for factorial of 4. Each function call adds a new frame to the stack until the base case is reached. As the stack grows, memory usage increases. The stack growth indicator illustrates how the stack expands with each recursive call, while the memory usage indicator shows the corresponding increase in memory consumption. Let's look at a practical example with different space complexities. The problem is to find two numbers in an array that add up to a target value. In the naive approach, we use a hash map, or a dictionary, to store previously seen values, which requires O of n extra space. For example, consider this Python function toSum, where a new dictionary is created. This approach has a space complexity of O of n. For sorted arrays, we can use a two-pointer approach that moves inward, requiring only O of 1 extra space. Consider this Python function toSumSorted, which assumes that the input array is sorted. This approach has a space complexity of O of 1 because it utilizes only constant extra space. Different data structures have different space complexities. Common data structures like arrays or lists have a space complexity of O of n because the contiguous block of memory grows linearly with the number of elements. For example, consider this Python list nums that contains 5 elements and occupies 5 units of space. Hash tables or dictionaries also have a space complexity of O of n because key value pairs are stored using a hash function, and the space grows with the number of entries. For example, see this Python dictionary student, which stores the student ID, name, and grade. Trees have a space complexity of O of n. It is a hierarchical structure with nodes and edges where total space is proportional to the number of nodes. Graphs have a space complexity of O of v plus e, where v is the number of vertices and e is the number of edges. A graph consists of a collection of nodes, or vertices, connected by edges. Now let's examine space-time trade-offs in algorithm design. One common trade-off is trading space for time, where we use more memory to achieve faster execution time. For example, memoization is a technique where we store previously computed results in memory to avoid redundant calculations. Another common trade-off is trading time for space. This is where we use less memory at the cost of increased computation time. For example, recomputation involves recalculating values instead of storing intermediary results in memory. When should we optimize for space? We should optimize for space when we have limited memory environments, such as embedded systems or mobile devices, large datasets that exceed available RAM, distributed systems with memory constraints, applications with many concurrent users, or when memory allocation or deallocation is costly. When should we optimize for time? We should optimize for time in real-time systems with strict timing requirements, user-facing applications where responsiveness matters, when processing power is the bottleneck, systems with abundant memory resources, or computationally intensive algorithms. Let's analyze the Fibonacci sequence calculation using different approaches. The problem is computing the nth Fibonacci number with different approaches. The first approach is a recursive approach that has a space complexity of O of n. It is a classical recursive implementation that uses the call stack for storage. Here, consider this Python function Fibonacci recursive of n. Despite its elegance, this approach has O of n space complexity due to recursive call stack frames. The pros of this approach is that it has simple and intuitive implementation, it has direct translation of mathematical definition, and it has clean readable code. But it has some cons, such as it has O of n space complexity due to call stack, it has exponential time complexity of O of 2 to the power of n, and stack overflow can occur for large n values. Let's consider an iterative approach which has a space complexity of O of 1. This is a bottom-up iterative implementation that uses only a constant amount of extra space. In this Python function Fibonacci iterative of n, this approach uses only 2 variables, regardless of the input size, achieving O of 1 space complexity. The pros of this approach is that it has constant O of 1 space complexity, it has linear O of n time complexity, there is no risk of stack overflow, and it has faster execution for large inputs. The cons are that it has less intuitive implementation, it has slightly more complex code, and is not as directly tied to the mathematical definition. Here are some best practices for space optimization. Use in-place algorithms which modify input data structures directly instead of creating new ones when possible. Release resources early. Deallocate memory as soon as it's no longer needed in your program. Process data in chunks. For large datasets, use streaming or batch processing instead of loading everything into memory. Use appropriate data structures. Choose data structures that minimize space overhead for your specific use case. Avoid deep recursion. Convert recursive algorithms to iterative ones to eliminate call stack overhead. Use lazy evaluation. Compute values only when needed instead of pre-computing and storing everything. Remember, space optimization depends on your specific context and constraints. Balance memory usage with other considerations like readability and maintainability. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.